The final rule in our set of derivative rules is going to be the chain rule. And the chain rule lets us combine functions like the product and quotient rule, except that here we're going to have functions that are nested one within the other. And there's some symbolic ways to represent it, and you can refer to the textbook to get a little more explanation on that. But it's almost easier to see it in practice. So let's just take a look at this version of the formula. The idea is you have a function of another function, and let's actually take a look at the next page to see an example. Here we have e to the x squared. So this would be g of x, the inside function, and e to the x would be the outside function. I'm taking e to the something, and that something is complicated. It's not just x, it's an x squared. So if we have that scenario and we're asked, hey, what are the slope values for that function, or what's the derivative of that function, this is the rule we can apply. We'll take the derivative of the outside, and we'll put outside in quotes here. Sometimes it'll be obvious that it looks outside, sometimes it'll be less so, but it's the function that gets applied last, times the original, or using the original inside, and then we multiply by the derivative of the inside. All right, so that's one way to try to remember it. Again, in practice, practice is the best aid for this. So let's take a look at some examples. Our function is e to the x squared, and we're asked what's the derivative of that. Well, our outside function in this case is e to the something. So let's write this out in long form here. The derivative of e to the x squared, there's our inside function, x squared. The derivative, this is the way I like to say it, everyone has their own style, but the derivative of e to the x is e to the x. Another way to phrase that in a chain rule world is the derivative of e to the anything is equal to e to the anything. So all the rules we learned before, derivative of e to the x is e to the x, keep the same structure, except that whatever we have that's more complicated inside just stays where it is. It takes the role of x in our functions, except that the chain rule is going to tell us to take the derivative of that inside or that anything. Okay, how does that play out in practice here? The derivative of e to the anything is e to the same thing, again, times that expression here differentiated. So times 2x here. So e to the same thing again times 2x. And you might ask, well, how often do I keep doing this pattern? Well, there's no inside function here anymore. So there's no other way to think of the chain rule applying. So we just stop at this particular point here in this calculation. Let's do some more and see how the patterns work out. Here we very clearly have an inside function with the x to the 4, and the derivative of ln of x is 1 over x, and so the derivative of ln anything is 1 over that same thing times the derivative of that same thing, of the anything. This is very technical language. I hope you all appreciate that. All right. So derivative of ln x is 1 over x. The derivative of ln x to the 4 is going to be 1 over x to the 4 times, don't look at where it is here, go back to the original function and take its derivative. So times the derivative of x to the 4, which is 4x cubed. And if we simplify that out, that actually turns into be 4 over x. That seems maybe a little simple at first glance, but do remember, actually, we could rewrite this using log rules. we could bring that 4 down front using the log rules and say, hey, what's the derivative of 4 ln of x? Well, hey, that's 4 times the derivative of ln, which is 1 over x, and whew, our two different methods, one using the chain rule, one using log rules, both lead us to the same solution, to the same value for the derivative. So that's an excellent reinforcement. All right. This one's a little less obvious. You might think quotient rule at first, but quotient rule is actually overkill for this. When we have a constant numerator, the quotient rule can actually, it's easy to make silly mistakes because the derivative of the top is just 0. So another way to do this is to rewrite as a power. So if we take the derivative of 1 over 1 plus x cubed, another way to write that is 1 plus x cubed all to the negative 1. With that expression, then we very clearly have an inside function and an outside function. And our rule for any power is bring the power down front, keep the same thing inside, subtract 1 from the power. So that's our derivative of x to the p is p x to the p minus 1. And then we multiply by the derivative of the inside. So there's our inside. We're going to multiply by that derivative, and that derivative is 0, derivative of a constant, plus 3x squared. And wouldn't hurt to tidy that up a little bit. We have a negative and 3x squared, and this is all to the negative 2, or we could write it as 1 plus x cubed squared, but in the denominator. So the derivative of 1 over 1 plus x cubed does have sort of a quotient rule feel to it because of the quadratic in the bottom, but I think this method is a little more straightforward than the full out top derivative times the bottom, all that for the quotient rule. This seems a little more efficient to me. You would get the same answer both ways, but it's up to you which method you choose. All right, a little more practice. Don't forget the easy rules. Here we have a simple derivative of x to the fourth, which would have a derivative of 4x cubed. And now we have a derivative of a different kind of exponential, but again, it's like e to the x, or it's a different base though. The derivative of 10 to the anything will be 10 to the same thing again times ln 10. So that is from the derivative of 10 to the x. The only change is that 3x there. But then we have to multiply by the derivative of the inside function, and the derivative of that inside function is simply 3. The derivative of 3x is 3. So here you have to be careful. There's one factor that shows up because of the 10 to the power derivative. There's another factor that shows up because the exponent wasn't simply x, it was 3 to the x. And not a whole lot of tidying that can be done here, but we can at least reorganize. Like so. Finally, here's a quick practice exercise if you want to give it a shot. The derivative of e to the root x is which one of these values here? I'll give you a moment to think about that, and then we'll tackle the explanation. Okay, so anytime, again, you see a square root, the easiest thing to do is to rewrite it as a power. So before we take our derivative, the best thing to do to make your derivatives easier is to rewrite it as a power. Once we do that, then we very clearly have a chain rule. We have e to the x to the 1/2. The derivative of e to the anything is e to the same thing again, times the derivative of what was in the exponent. And we know the rule for powers of x is bring the power down front and subtract 1 from the power. And if we rewrite that a little bit, we'll have 1/2 e to the x to the 1/2, or e to the root x, times x to the negative 1/2 That's 1 over root x. And that matches perfectly with number 3.